Certain polar equations have special names. Definition of a limacon in polar coordinates says a limacon is a figure with polar equations r equals a plus b cosine theta or r equals a plus b sine theta. And then depending on the absolute values, if the absolute value of a is less than b, it's going to have an inner loop like this one. If the absolute value of a is greater than b, then it will have no inner loop and it will actually kind of more flatten out on the one end. Okay, kind of look like a flat tire in a way. So think of a circle that flattens out, but then is round on this side. And then if the absolute value of a equals the absolute value of b, then the limacon is going to have what's called a cusp at the pole. And a cusp is basically a point at which the graph of relation changes abruptly. All right. So that's a limacon. Now, if you graph the reciprocal of the polar equation of a limacon, the result is surprisingly a conic section, which might surprise you if we had covered conic sections, but time didn't allow us to get to that. So conic sections in polar coordinates says the general polar equation of a conic section with the focus at the pole is r equals k over a plus b cosine theta or k over a plus b sine theta. Eccentricity, again, isn't going to mean anything to you because we haven't covered it. Basically has to do with the curvature. The eccentricity of the conic section is b over a. I'm not really going to do anything with that, just showing it to you. K, absolute value of k equals the absolute value of AEP, where p is the distance between the focus and the directrix. If the absolute value of b is greater than a, it's an ellipse. If the absolute value of b or less than a, it's an ellipse. Is greater than a, it's a hyperbola. If absolute value of b equals a, it's a parabola. Ellipses are kind of like circles, only they're more egg-like, so they're not exactly round. So if you elongate one side, you get an ellipse. Parabolas, hyperbolas, I mean, are kind of like parabolas that are facing each other. That's kind of how they look. There are other curves that can be graphed, such as roses, which will look something like this. Spirals, which will look something like this. Cardioids, which is heart-like. All these different types of shapes can be graphed. And I always have put this, think spirograph. And we used to have an old toy called a spirograph, and they have these little gears, and you put these gears inside this thing, and then you put your pencil inside the gear, and you spin it around and around and around, and end up drawing one of these things. I don't know if you know what a spirograph is or not. Every year I've had somebody know what it is, so I'm just kind of throwing that out there. But for our problems, what we want to do is we want to take our calculator and we want to get it ready to graph in polar mode. So to do that, you're going to hit the format, which is up here, okay? And you are going to switch to polar graphing coordinates, okay? And now, when I go to y equals, actually, I'm also going to have to switch my mode to degree and POL, polar. So now when I go to my y equals, it's not y equals anymore, it's r equals. And r equals 6 sine 5 theta, 6 sine 5 theta. Your variable key isn't x anymore, it's theta. And you close that out, okay? Our window will let be, since it's theta, we'll let it be an angle 0 to 360 with a step of, I don't know, maybe 2 degrees or so. X, we'll start off with the negative 10 to 10 by ones, and y will start off with the negative 8 to 8. by ones. And we graph this and we end up with a 5-leaf rows as it says. I'm going to end this video and come back just because this one's getting long. And we'll deal more with this.